Welcome back to the control system series. In this session, we are going to discuss four essential stability analysis tools. The first one, Raut Arwitz criterion. The second one, root locus. Both are used in time domain response analysis. And third one, Bode plot. And the last, Nyquist plot, where it was predominantly used in frequency domain analysis. The time domain analysis shows how fast the system responds, where the frequency domain analysis shows how well it handles different frequencies. Together, they form the foundation of control system design. A system is stable if all the poles of its closed loop transfer function lie in the left half of the S plane. So our goal is to find whether any poles move into their right half. That's where the instability begins. We know that time domain analysis uses standard test inputs. Let's first start with algebraic method, the Routh-Hurwitz criterion. It helps us determine the number of roots of a characteristic equation that lie in the right half of the S-plane without actually solving the equation. We are form a router using the coefficients of the characteristic equation. Then by checking the sign changes in the first column, we can determine the number of roots in the right half of the plane. Now remember, no sign changes in the first column. The system is to be stable. Each sign change, one right half of the plane root exists. Zero in the first column, maybe it will was marginal or special case. So we have to focus the first column. The Routh-Hurwitz test tells whether the system is stable, but not how the folds move as gain changes. For that, we use the graphical tool, the root locus method. The next technique will be the root locus method. Root locus technique shows how the roots of the characteristic equation move in the S-plane as a system parameter. Usually, gain k varies from 0 to infinite. For a feedback system, the characteristic equation is 1 plus g of s h of s equal to 0. The root locus plots the solutions of this equation as gain k changes. The root locus follows simple rules. It starts at open loop poles k equal to 0 and ends open loop zeros where k equal to infinite. The number of branches is equal to the number of poles. Symmetric about the real axis, and the real axis segments exists to the left of an odd number of real poles and zeros. Asymptotes shows where branches go to infinity. By observing the root locus, we can predict when poles cross the imaginary axis, which marks the onset of instability. This helps in choosing the right gain for desired stability. So we have to trace the pole trajectory for variation of k 0 to infinite. When the pole moves towards the right half of the S-plane, the system becomes unstable. So in short, Rao Hurwitz tells whether the system is stable. Root locus shows how the stability changes as gain varies. When we apply the sinusoidal input to the linear system, the output also sine, but many differ in amplitude and phase. Studying these changes across frequencies gives us the frequency response. A body plot is simply a graph that shows how the system's magnitude and phase vary with the frequency. Using logarithmic scales, it has two parts: magnitude, usually represented in decibels, and the phase in degree. Let's consider the transfer functions. G of S, we have to convert it into frequency domain, so we have to substitute S equal to j omega. By substituting j is equal to j omega, we can convert the transfer function from S domain into frequency domain. So we get the frequency response as g of j omega. Then we find the magnitude by using the logarithmic form. So board plots make it easy to analyze complex systems, approximate higher order functions, and determine gain margin and phase margin for stability. Let's see the stepwise approach to construct the Bodo plot. First, we have to convert the S plane into frequency response by substituting S equal to j omega. Then we have to identify the corner frequencies. And then we have to start to plot the magnitude by using the slope rules. Then we have to sketch the phase curve for the lower, higher, and the corner frequencies. Refine with exact values if needed. Now comes the key part, the stability analysis. From the body plot, we can find the gain margin and the phase margin. The gain margin is nothing but how much gain we can increase before instability. It was measured at phase minus 180 degree. And then the phase margin is how much phase lag can increase before the system unstable. When measured at gain 0 dB. So the larger gain or the phase margin means a more stable and robust system. When the phase margin and gain margin are small or negative, the systems shows the instability. When the phase margin is equal to gain margin, the system is marginally stable. So remember, when we apply a sinusoidal input to a system, the output has the same frequency but different amplitude and phase. The Nyquist plot captures these changes as a continuous curve in the complex span as frequency omega varies from 0 to infinite. Nyquist plot is a polar plot of the open loop transfer function g of j omega and h of j omega. Where the x-axis represents the real part and y-axis represents the imaginary part. As frequency changes, the tip of the vector j of j omega traces a path that's the Nyquist curve. We uses the Nyquist stability criterion to determine whether a closed loop system is stable based on how the Nyquist plot encircles the critical point -1 plus j 0 in the complex spinning. To draw an Nyquist plus, first we have to substitute S equal to j omega So we can transform from S plane to the frequency domain. Then we have to compute the magnitude of g of j omega for a range of omega varies from 0 to infinite. If g of s has poles on the imaginary axis, use small semicircular detours around them. Complete the plot using the symmetry about the real axis. The Nyquist criterion states n equal to z minus p, where n is number of clockwise encirclements of critical point, where p number of open loop poles in right half of S plane, and z number of closed loop poles in the right half plane, that is unstable poles. If z equal to 0, the system is said to be stable. If the Nyquist plus passes the right of minus 1 comma 0, the system is stable. If it is passes through or encircles the point clockwise, instability occurs. From the Nyquist plot, we can also estimate gain margin, the inverse of g of j omega. So by using the gain margin and phase margin, we can also predict the stability of the system. While Bode plot gives the magnitude and phase separately, the Nyquist plot combines both a single complex plane curve, giving a complete view of how gain and phase interact. Let's summarize. The Raut array criterion allows us to determine the stability without solving for poles. We form a Raut array from a characteristic equation and check sign changes in the first column. So no sign changes, the system will be stable. When there is a sign change, the system becomes unstable. When the zero or auxiliary polynomial exists, it will be marginally stable. The root locus shows how poles moves as the system gain changes. It's a graphical method to analyze stability margins and design controllers. If we check if Loki cross into the right half of the plane indicates instability. The Bode plot shows the magnitude and phase versus the frequency. Stability is determined using gain margin and phase margin. For the positive margins, the system will be stable. For the negative gain margin and phase margins, the system is said to be unstable. The Nyquist plot maps g of j omega h of j omega, that is Lyapunov transfer function, in the complex plane. When n equal to p or z equal to 0, the system will be stable. Or no encircled when means stable. In real life, stability analysis ensures the safety and reliability of systems, from aircraft, fighter pilots to industrial robots and medical devices. Without it, system could oscillate, overreact, or even fail completely. So remember, stability means every system eventually settles down. By analyzing poles, margins, and responses, engineers make sure the system performs exactly as intended. Thank you.